Hello friends, welcome to channel Crash Course for the Engineers. In today's session, we are talking about simple vapor compression refrigeration system. The vapor compression refrigeration system is the improved type of air refrigeration system. Now the difference is in case of air refrigeration system, air refrigeration system, the working fluid refrigeration system, air is used as a working fluid. Now, in case of the vapor compression refrigeration system, one new thing is introduced as a working fluid, working substance, and it is called as a refrigerant. Now, uh, this refrigerant condenses and evaporates at the temperature and pressure which are nearly equal to the atmospheric conditions. Normally, we use ammonia, then CO2, that is carbon dioxide, then sulfur dioxide. These gases as refrigerant. Uh, the difference between air refrigeration system and vapor compression refrigeration system is that the refrigerant does not leave the system, but it is continuously circulated throughout the system uh, so that it will have the effect of condensation and it will have the effect of evaporation. And during this process, the latent heat in the evaporation or evaporator, it absorbs the latent heat from uh, from cooling space, cooling space in many of the applications you will find instead of cooling space there is a uh, brine solution which we call as a secondary refrigerant. So it will absorb the latent heat from brine solution or from the cooling space. And in case of the condenser, it will reject heat to atmosphere, atmosphere or if there is a any cooling medium other than air or atmosphere. Now, in today's world, uh, this a this vapor compression refrigeration system we find in many of the applications which range from the uh, simple domestic refrigerator refrigerator to the big big air conditioning systems. So, what are the advantages and disadvantages of vapor compression refrigeration system? Let's talk about the advantages. Advantages. Number one, uh, the size is small size for required required capacity. So the size of the system is small uh, for the required capacity. Next is the less running cost. Third, Uh, it can be used for a large range of temperatures. So applicable or can be used for large range of temperatures. And next one, which is very, very important, that the coefficient of performance, that is COP, is high. Now, these are the advantages. Now, talk about the disadvantages. Disadvantages. The first disadvantage is the initial cost is more. So, initial cost is high, and we can say that the prevention of leakage of refrigerant is difficult, or is or is major problem. So, as compared to the disadvantages, we know that the advantages are more. That's why in most of the industrial applications, in most of the household applications, you will find the vapor compression refrigeration system. Uh, the refrigerant may be different, but it will be used. Now, how it works? How it works. So, understand, friends, uh, uh, with the working, I'll explain the processes on the pH and TS diagram. Now, let us see the diagram. Now, I hope that you can see the diagram. So, this is the diagram of a vapor compression refrigeration system, and one by one, we'll understand the working. So, first component in the system is the compressor. Now, the refrigerant, which is the working fluid, uh, enters into the compressor. Mostly, if we talk about the domestic air conditioner, refrigerator, it is a hermetically sealed compressor, reciprocating type. So, the refrigerant enters, it will be compressed, and at point B, it leaves the compressor. So here you can see this. This is the high pressure line. There is a pressure gauge which we can install to measure the pressure. So the refrigerant which is leaving the compressor is is high pressure at high pressure and high temperature. So let us draw these processes on the pH and TS diagram. Let us see the processes on pH and TS diagram. So suppose this is pH and this is TS. So now, okay. So the process of compression, as I'm telling you, the process of compression is ideally it is isentropic process of compression. So we can say the process is 1 to 2, and so it can be shown on TS diagram by a vertical line. Here I am assuming that the vapor which is entering into the compressor, it is dry saturated. So process 1 to 2. On pH diagram, it may be like this. 1 to 2. So this is 1 and this is 2. This high pressure, high temperature refrigerant enters into this condenser, wherein uh, wherein it will reject heat to the cooling medium, and during this process the temperature. Okay, so the process of condensation is a constant pressure, constant temperature process, ideally constant pressure and constant temperature process, in which the latent heat rejection will take place. The refrigerant will give away its latent heat to the any cooling medium that is being used. So after the process of condensation, it will be high pressure liquid vapor mixture. So that process can be shown on the TS diagram like this. On pH diagram, it can be shown like this. Okay. Then this liquid refrigerant is collected in the receiver. The function of the receiver is to just collect the liquid refrigerant. Apart from it, it is not having any uh, function. So condensed liquid refrigerant from the condenser is stored in the vessel, which is known as the receiver, and it is supplied to the expansion valve. Now, this expansion valve is a tube. Mostly in case of domestic refrigerator, we use capillary capillary tube as expansion device, and in bigger size applications, we use different kind of expansion valves. Now, friends, the process of expansion is an isenthalpic expansion. So, on pH diagram, it is shown by vertical line where the enthalpy is constant. On TS diagram, the process is shown by a dotted line. Okay, so the entropy will increase during this process. Now, this uh, refrigerant, which during this process of expansion, the pressure of the refrigerant drops, and because of the temperature of the refrigerant also drop, and it will be a mixture of liquid and vapor. Now, this liquid vapor mixture of the refrigerant enters into the evaporator, which is insulated cold chamber, and it will absorb the heat. It will absorb the heat from the uh, cooling chamber, and its temperature, it will absorb the heat, and this heat is a latent heat. Okay, so this process 4 to 1 is the process of evaporation, wherein the uh, refrigerant absorbs the heat, keeping its temperature and pressure constant. The latent heat absorption takes place. Okay, and after the process of evaporation, this low temperature, low pressure refrigerant goes through this low pressure side, enters into the compressor, and it will be compressed, and the cycle will continue. Okay, as I told you that there is a high pressure gauge on a high pressure side, there is a vacuum gauge on a there is a vacuum gauge on low pressure side also. And the functions of the pressure gauge is to uh, take the note of the temp pressure. Okay. Now, as we have seen this diagram, let us talk about the coefficient of performance. So I'll slide a little bit so that you can see the things. So uh, coefficient of performance is a ratio of the refrigeration effect divided by work done. Now the refrigeration effect or cooling effect process is 4 to 1. So H1 minus H4 is the refrigeration effect, and the work input is H2 minus H1. But as you can see on the uh, pH diagram, H3 is on the liquid line. So H3 can be easily found out. Finding value of H4 is not easy, but uh, we know that this process 3 to 4 is isenthalpic expansion. So H3 will be equal to H4. So the relation can be modified as H1 minus HF3 divided by H2 minus H1. Now, friends, this is the coefficient of performance, and uh, for vapor compression refrigeration system, uh, I have done some assumptions. Assumption was very simple that the refrigerant after the process of compression is at a superheated state, and because of this assumption, I have plotted the pH and TS diagram like this. Okay, so during this explanation, I have covered the types of vapor. In case of the types of vapor compression cycles, we have a cycle with the superheated vapor after compression, and I have done the analysis of this superheated vapor after the process of compression. Now, let us talk about the next cycle. The the things will remain the same, the working will remain the same, just only change will with the refrigerant which is entering into the compressor. If it is dry saturated vapor, if it is a mixture, uh, that is wet vapor, or it is superheated vapor before the process of compression, or there is a subcooling or superheating. These things will change the refrigeration cycle, and these values of the enthalpies uh, uh, progressively. So that's why let's talk about the first cycle where uh, the refrigerant is dry saturated vapor after compression. So dry saturated saturated vapor after compression. Okay, I'm using short form. So this theoretical cycle, these are all theoretical cycles. Now let us see the notations I'm using are the same. So this is the uh, dome, and this is pH, and this is TS. Okay. So first, uh, the refrigerant which is uh, exiting the compressor is at saturated vapor. So point two we are drawing first. So this is the point two. It means that the refrigerant will be inside the dome during the process of compression. So point one will be the mixture. Okay. So 1 to 2 process isenthalpic. It is isentropic compression. So S1 is equal to S2 is plotted on the TS diagram, vertical line, and on pH diagram it is a slant line, or in many of the books it is curved line. After there is a process of condensation 2 to 3. The process of condensation is like this, 2 to 3. Then process of expansion, which is isenthalpic, 3 to 4. Process of expansion, 3 to 4. And lastly, 4 to 1 is the process of evaporation. Okay, so the COP for this cycle, you can easily understand that COP is equal to H1 minus H4 upon H2 minus H1. So H1 minus H4 will be HF3 and H2 minus H1. So this is the vapor compression refrigeration cycle where it is a dry saturated vapor after the process of compression. Friends, related to the numericals on this part, in one session you will find that the numericals are solved. Next cycle, let us talk about important cycle, that is vapor compression cycle with wet vapor after compression. So wet vapor after compression. Okay, so let us first draw the pH and TS diagram. Okay, so this is pH and this is TS. TS. This is the dome. Now the refrigerant is wet vapor after the process of compression. So point 2 lies inside this dome. Point 2 lies inside this dome. So the process of compression on TS diagram is very simple, 1 to 2, and on this like this. Okay. Then process of heat rejection or condensation 2 to 3 like this, and uh, isenthalpic expansion 3 to 4, and heat absorption, expansion, and heat absorption. The formula will remain the same. So COP is equal to H1 minus H4 upon H2 minus H1. So H1 minus HF3 upon H2 minus H1. Friends, while solving the numericals, we will understand the effect of all these things on this cycle, so that we can compare these cycles and we can find out which cycle is good for the overall refrigeration system. Now, uh, now let's see the next cycle wherein the superheated, so superheated vapor after compression vapor. Okay, so after compression we have covered. So before compression. Okay. So here this is the PS and TS representation. Okay. So the vapor is superheated before the process of compression. So point one we are talking about is in the superheated region. When the process of compression takes place, so like it will be a vertical line, pardon me, okay. Yeah. So this is 1 to 2 and this is 1 to 2. Then the process of condensation here 2 dash and 3. During the process of condensation on the TS diagram, first the temperature of the vapor will reduce to the saturated state, so 2 dash, and then constant temperature heat rejection will take place in the condenser. After that, the process of isenthalpic expansion 3 to 4 and TS, this is the isenthalpic expansion. The last process is the heat absorption. The heat absorption in case of the pH diagram is a horizontal line where I need to plot 1 dash. On the TS diagram, it should be a horizontal line till the saturated dry state. After that, there will be a increase in the temperature of the vapor refrigerant. And what about the COP? So COP, I hope that now you have memorized the formula. So H1 minus HF3 divided by H2 minus H1. Now, friends, there is one process which is called as undercooling or subcooling. So, vapor compression cycle with uh, I'll say I'll take the number. So 4. So it is 4 with vapor compression cycle with under cooling or sub cooling. Now, during this cycle, what we do, the refrigerant which is leaving the condenser, it is cooled to certain temperature, and this cooling process takes place. Uh, the reduction of the temperature below the saturation temperature. Okay, so that's why this is called as a subcooling or undercooling. Now let us see how it takes place. Uh, this is a very important process in case of the refrigeration cycle, PS and PS. For this, we are assuming that the refrigerant which is entering into the compressor is dry saturated state. So point one is over here. The process of compression is a vertical line. Okay, and like this, 1 to 2 to dash. Then here is the point 3. So I am plotting on the TS and pH. So 1 to 2 to dash and now, as I told you, this refrigerant is undercooled after the process of condensation at constant pressure. Its temperature will is reduced. Uh, so this point 3 here lies in the liquid region. And in case of uh, the TS diagram, the temperature is dropping. So this 3 dash 3 dash is like this on the TS diagram, but on PS diagram it is shown in this way. Okay, so what we do will then the process of expansion takes place. Sorry, just let me draw. Okay, so this is point 4, and here it is the process of evaporation. Now this is point 4, and this is the process of evaporation. Now if I compare with the original cycle, here it will be point 4 dash in the original cycle, and on the TS diagram it will be like this. So let us see the COP. COP will be equal to H1 minus HF3 divided by H2 minus H1 in the original cycle, and in case of the undercooling or subcooling, COP will be equal to H1 minus H3 dash divided by H2 minus H1. So here the length of the line, that is 4 to 1, is more than 4 dash to 1. It means that for the same capacity of the compressor, we are getting more refrigeration or the cooling effect. So these are the things which are used to increase the refrigeration effect, keeping other things constant. Now, friends, these are the basics related to the basic cycles related to the simple vapor compression refrigeration system. Other things related to it will be covered in the portion on the numerical, so that you will understand numerically with the values. Uh, I hope that you are understanding the content I am covering during the sessions. If you have any query, please comment. If you want some another uh, content related to the topics, please post it in the comment. If you like the content, please subscribe the channel. Thank you, friends. Thank you for watching the video.